Hello, everybody. Any doubt?
Hello, sir.
Yeah.
Uh, in the quiz, there were many questions where we had to interpret the transfer function, maybe to get the settling time, rise time, or something.
Yeah, yeah.
So,
Okay.
can you please tell all those variations how to interpret the transfer function and get different things from it?
So from the transfer function, the finding out the settling time and all those that you are saying.
Maximum overshoot,
Yeah.
delay
So
time.
yeah, for those there is like you have to understand what is the meaning of like maximum overshoot. So the meaning is like of this is for second order system, right? So you have it goes like this, right? So first you have to find out where this happens, and then you put the value accordingly that you will get there. So I mean, this we have done earlier also. So in this in vibration also you get the same thing. Like in the second order system, like a string mass campus system will like this one, right? If you have like this one under time system, so if you give a step input, right? So if force is ft is like this one, then the displacement will go like this. And how to do it? Was when you have xt, you have some expression for that, right? So at this point, what happens? At this point, the slope will be 0. Yeah, so you make a dx over dt equal to 0, and this will give you the peak time, right? So this is what we call it peak time, right? Okay, so you solve for t at here, you will get the peak time, and then xtp is going to give you this one, right? This is what the peak x peak, right? This is the peak, and the in this one is the mean time about which it is going to be settled finally. Yeah, so the peak will give you in that case will nothing but xp minus for unit step function. This will be the one you let us say call it x naught. So this x naught. So this is what it is going to be the overshoot, right? So this is going to be overshoot. Typically x not equal to 1, then you have like then this RT has to be equal to CT, right, at the steady state. So in that case, this will be 1, and then you will get the maximum overshoot, this one. So which part you are not able to understand?
We were given second order transfer functions.
No, so could you please again? Yeah, say again.
So we were given second order system transfer functions,
Okay.
and from the transfer function we had to tell what is the maximum overshoot.
Yeah. Okay.
So what exactly to do there? I mean, I did not understand that.
Okay. So did you see the lecture videos? Yes or no?
Yes, sir.
Yeah. So did I not explain that?
Sir, I may have forgot.
No. So all these things are already there. You know, whenever you have a transfer function, what is the meaning of that? I mean, you are asking very basic question that say if you don't understand that, you are not able to solve anything. So any transfer function, if Ts equal to omega n square over s square plus 2 zeta omega n plus omega n square. If you have like this one, then what happens? This is Ts. This is the transfer function. You have input and there is an output. What is the input? Input you call it Rs, the output is Cs, right? So how they are related? Ts equal to Cs over Rs, and which is equal to omega n square over s square to zeta omega n square. Yeah, so this is how this one is. So Cs is equal to n square over s square plus 2 zeta omega n plus omega n square times Rs. Now, what we are doing, Rs is a unit step function. Rs will be equal to 1 over s. So here it will be omega n square over s square plus 2 zeta omega n plus omega n square divided by 1 over s. And then you are getting Ct. Ct equal to, make inverse of that. Okay, so omega n square over s multiplied by s square plus 2 zeta omega n plus omega n square. If you take Laplace inverse of that, you will get Ct. And that Ct, you will, if this is RT, right, you will get a Ct which will look like this one. And from here, you have to get all those things. What is what? I have explained already, so this today I would like to more answer from the chapter 7. It's a difficult, this already we have done already, and it is coming twice. This kind of thing we have also seen in during vibration, and again it is coming here. So I suggest you see the lecture videos, so it is not just in like a few minutes I can explain that. So those things, whatever I ask the questions, have been there in the lecture video. So you have to watch the lecture videos first. First you watch that. If I'm not able to understand, just let me know. Okay, then I can explain. But things that most of students will be knowing already, all those things, I don't want to repeat here, because I want to give time on something which is more difficult, and like chapter 7. This is more about chapter 7. Yeah, so did you get it?
Sir, thank you.
Yeah, okay. So please see the lecture videos. Everything is explained already. Yeah. Yeah, okay. Yeah, so the first comment, please explain the question in the quiz where we were asked to tell the system was stable or able to do the parts in which 0 was coming. I was not able to get Nyquist criterion properly. Please tell what are the steps to be followed to stability by Nyquist stability. Okay, first of all, regarding the quiz, okay, so what I will do, maybe I will make a video for that. Yeah, so quiz questions. Yeah, so that way I don't want to repeat all those things here. I want to focus here on the chapter 7, because that is more important and all. Yeah, so regarding the quiz questions, I will solve it either on video, or I will see what way it can be done. So accordingly I will do it. Okay, so no quiz questions here, please. Yeah, so that I will take care. I will send the solution either in video form, or maybe I solve it like that. Okay, so yeah, so next thing is okay, so Nyquist stability criteria. I was not able to get Nyquist stability criterion properly. Please tell that what are the steps to be followed to check stability by Nyquist stability. Okay. Okay. So before we go to question 15. Okay. Yeah. So okay, Nyquist steps basically is, first you have to plot the Nyquist the plot. Yeah, so this how do you do that? So here there's a mapping, right? First you see a mapping. What is the mapping? In S, this is S plane, yeah, from S plane, and this is R, which is infinity, S to infinity. Yeah, so it goes for like this one, clockwise, yeah, and this is 0, like that. And here you are mapping of what? Let us say you have GS, right? You have GS. So GS is the open loop transfer function. Open loop transfer function, and you are going to plot GS here in the GS plane. Yeah, G plane you can say here, right? Okay, now this then you are going to plot some bit. So maybe you are plotting, it goes like this one, it goes like this one. Yeah, so uh, you are plotting what? G I omega. Yeah, what versus what? You are this point, this, let us say this is point, this is a point, G I omega point, and that really means from here to here, the radius will be G I omega. Okay, radius will be that, and the phi, and this phi will be angle G I omega. Right? So this is what the angle will be, and this radius will be. This is how you are going to do, and you are changing this point. Let's say point P. You are changing omega with that. Yeah. So when you change omega, accordingly you move like this one. Yeah. So once you have that, and then what do? You have to look for point the -1, -1 plus 0 I, right? This point, and you have to see basically where this point is. If this point is here or here, depending on that, stability will be there. Okay, so what does the Nyquist stability criteria says? You can sum it as n equal to z minus p. Yeah. Okay. So here it says number of encirclement. Clockwise encirclement is equal to number of zeros of this minus number of poles. Okay. Now, first you have to know that poles. This gives you the difference. Remember, right? That really means one of them you have to know. Then only you can predict. Otherwise, no point. So typically, it's known that poles are. You see, like poles equal to, there are no poles. You will see there is no poles, right? So say, let us say we assume that there is no poles on the right S plane. No poles on the right S plane. No pole of what? No poles of. So here, in this case, the poles has to be, in this case, since we are talking about all this, we are talking about regarding the open loop transfer function. So no poles of the open loop transfer function. Right? On the right is plane. If you know that, for example, then after that, what happens? N equal to Z only. Right? P, in that case, P will be equal to 0. If P equal to 0, that really means N equal to Z. So for example, here, if it is passes like this one, and if the -1 plus 0 I is point here, in that case, it tells you that there is 1 0. There is a 1 0 inside here somewhere. And since things are on the right S plane only, that indicates that this is, it will have 1 0. If there is a 1 0 on the right S plane, that really means the system is not stable. Right? So, okay. Let us say the point minus 1 point is here now. Then you have n equal to 0 in this case, right? Because it is not encircling minus 1 there. In that case, n will be 0. And hence, n is 0, so that tells you that g is also equal to 0, provided there is no, if it is known that there is no poles on the rightest plane. As you know that if there is a pole on rightest plane, automatically it tells you that there is some problem. Yeah. So this is how you are going to check it. So is it clear? Yeah. Okay. So if you see the lecture videos, I have gone very slowly. First explain the what is mapping, from there to this one, y minus 1, all those things. Yeah, no? So this is the, here you have to know to begin with there is any pole or not. That's very important. Yeah, so you have to know to begin with. Okay, now let's go to question 15. Okay, 15. Consider the unity. Okay, so here the question is like this. GS is given. GS is equal to 1 over S, S minus 1. Okay. Okay. And okay, and then we have to draw the Nyquist plot to begin with, of course, and then what? Okay, so now let's see. Okay, so basically what we have to do here is first you have to plot that, and remember that when S is 0, then what happens? This is not finite, right? Is not finite, and hence it is written that you don't use like you don't your S now will cannot be, if this is R tends to infinity, right? But here it cannot go pass through 0, and hence you have to make a small loop here, and that's why it is given like that. And that's I have told in the lecture videos as well. So you will have a small radius here. Yeah, so this R here, R equal to epsilon. Yeah, epsilon is very small, very small, you can write, right? Very small, right? Okay, now this is how it is. This is our S plane. First, we need to plot it. So how you plot it? So G I omega becomes 1 over I omega multiplied by I omega minus 1, right? So we can write it like equal to 1 over minus I omega 1 minus I omega, right? We can write like this one, same thing. Okay, and hence we have G I omega is equal to 1 over 1 over, and then we have this. The magnitude of that will be simply omega only, and of this will be root 1 plus omega square. Right? So this was our magnitude is. The angle of gi omega will be equal to angle of I omega multiplied by I omega, or write like this, minus I omega multiplied by 1 minus I omega, yeah, which is equal to, will be equal to 0, right? So 0 minus angle of minus I omega minus angle of 1 minus I omega, right, is equal to minus, and here what do we have? We have 0 minus I omega basically, right? Minus, and this one is nothing but tan inverse, you will say. Tan inverse, this is sine minus omega divided by 1, right? So, or equal to minus tan inverse. Here we have minus omega over 0, right? Minus, and this is simply, we have tan inverse minus omega only, right? Okay. So, when you see here, we have to also look for the angle, or what the meaning of the angle is. Yes, accordingly. So what it means here is, if you see the quadrant, we have to locate. We have to be careful with angle, and we know that in these two, right? In these two sign, the cos will be positive. The cos positive, and in this sign will be positive. Sign positive. This is my way of doing it. You have your own way. Okay. So what it tells is sign is negative and cos is positive. Like here, the sign is negative, cos is positive. Yeah, we had like this, right? So the sign is negative here, and cos is positive here, right? So we are talking about this one basically. So we can also write minus simply. We can write as minus, and this is what tells us is minus infinity, right? So, or you can write here like minus tan inverse infinity, right? Minus, here we have, in this case also we are talking about like this one, so we can just say minus tan inverse omega basically. So or here we get 90 degree, plus you get tan inverse omega, right? So that's what we get, this angle gi omega, right? So we did all those things so that we can plot it nicely. Okay, now this based on this one, we are going to plot the Nyquist plot, right? So we start with like this one. So, and here we have real of gi omega, and this is imaginary of gi omega. And we start from somewhere. Yeah. So of course at 0 we cannot do it. We can start from here. Here we have omega equal to epsilon, right? So, or the value is I epsilon, right? So omega equal to epsilon. Okay, so there the value will be when omega, we can write it here. So when omega equal to epsilon, then the value is z is equal to 1 over epsilon and 1 plus epsilon square, but simply this will be like this one, and this value will be very, since this epsilon tends to 0, this is a very high value. And okay, and what is corresponding angle? Corresponding angle you can find out. So corresponding angle z I omega will be equal to 90 degree plus tan inverse epsilon. The tan inverse epsilon is 0 only, right? It's equal to 90 degrees. It tells you 90 degree and infinite. Yeah. So okay. So a little bit more than 90 degree. Just you see, if you have epsilon very small, then it tells you the angle has to be more than 90 degree. Yeah. So more than 90 degree will be somewhere here, right? So this is 90 from here 90 degree. This will be more than 90 degree, and the magnitude is infinite. So you can say that the point, let us say it's here, and this point tells us this is equivalent to omega equal to epsilon. Right. Now, second thing we can do is omega equal to 1. Right. So say omega equal to 1, and what value it gives. At that, we will get a magnitude or gain is equal to 1 over 1 root 1 plus 1 is equal to 1 over root 2. Right? 1 over root 2. And so 1 over root 2, and what is the value of the angle? The angle will be, so at this omega equal to 1, angle will be equal to 90 degree plus tan inverse 1 is equal to, this is 45 degrees, so 90 degree plus 45 degree, so 135 degree. So it tells us at 135 degree, the value is 1 over root 2. So this will be something like, let us say this is 45 degree, right? So will be somewhere here. So this is 45 degree, and here it is distance from here to here is 1 over root 2. Yeah. Similarly, you can find that omega equal to infinity. At omega equal to infinity, this becomes 1 over infinity, so it becomes 0. What is this? This one, 90 degree plus tan inverse infinity becomes 90 degrees. So this becomes 180. So omega equal to infinity. This is the point. So this is the point which is omega equal to infinity. Right? Will be 0 and will be 180 degrees. So it is coming something like this one. So if you plot it, this will look like, the plot will be something like this. Plot will be something like this. Yeah. So it is coming like this one, right? So at omega equal to very small to omega equal to 1 to omega equal to 0. Yeah. Okay, and similarly you can draw for omega, negative omega. When you say, so this is omega equal to infinity, this will be same thing, will be for omega equal to minus infinity. However, the angle will be minus infinity. If you put here, the angle becomes this side. So 90 degree minus side it will be go. So it will be the 90 minus 90. So it becomes 0. So the value will be, it will go like this. Mirror image about the z, the imaginary axis. So it will go like this. Okay, this is how it will go. Yeah. So when omega is very small, what happens here? This becomes 0. It will be simply 90 degree only. So you can repeat the same thing. You will find the Nyquist plot will be something like this only. Okay. Now once you have the Nyquist plot, you have to see whether it goes through -1 or not. And we can see here, in order to go to -1, you have to, let us say -1 will be somewhere here. It will not cross -1 because at 180 degree, you know that it becomes 0. So it will be going up. It is not going to cross it. So this is tangential here. It is not going to include this one, -1 point, right? Because phase is the 180 degree when you have omega equal to infinity, right? And when you have omega less, then phase angle will be even less, and hence it is not going to cross that. It will be going to away from that. That really means n equal to 0. That tells you that it is not in circle. So n equal to 0. That we know from here. Now, the rest of the things we have to read what is given there. It says, consider the unity feedback system with following this one. Suppose that we choose the Nyquist path as shown in figure this. Draw the corresponding G, J, omega locus in GS plane. Using the Nyquist stability criterion, determine stability of the system. Okay. Now let us see how can we guess. So here I'm going to delete this side. So from here we get n equal to 0, right? So now, looking at this one, we know that 1 over s is -1. What do we get? We get basically although we have moved this side, right? We have moved this side, and hence we have, if you see, the pole of that is at 1 somewhere. So this is at 1 point. We have a pole here. So we know that there is one pole, right? We have skipped this point 0, right? So we are not counting that. This tells you that pole at 0, right? And this tells you pole at 1, right? So since we have skipped this one, we have bypassed this one. Hence, this we are not going to count, but this is we are going to count. S -1, so pole at 1 is there. So this is, so here that really means from here we know that this tells you that P equal to 1 for sure, right? There is one pole here. There is one pole here which is inside this loop, right? Okay, this is inside this S contour, right? So we know that P equal to 1, I said, and N equal to 0. That we know from the Nyquist diagram. Number of encirclement of -1 is N, which is 0 in this case. And here we know that pole equal to 1 on the right S plane. Hence, N equal to Z. It tells you N equal to Z minus P, right? And from here, we know that since Z equal to, we don't know, but -1 is equal to 0. That tells you that Z equal to, there is 1 0. That tells you simply that there is 1 0 on the inside this one, that it tells you. Yeah. So is it stable or unstable? This is not stable. Why? Because there is a pole right side, because pole P equal to 1, and z is also equal to 1. So there is 0 also, the pole also on the right hand side on the S plane, hence not stable. Okay, got it? Yeah.
Sir, you had told that for the characteristic equation 1 plus T naught S or 1 plus GS, we'll have this will tell the zeros and the roots for that. So, sir, if we are having K upon S into S minus 1, then how will we see from that? Or
No, this is
is it a way to check?
Yeah. No. This does not tell you anything about K. Right now, K equal to 1 only. You are getting all those things for K equal to 1. Yeah. This is not about the root locus. In root locus, you explore the values of K. In this case, K is, you can assume K equal to 1 only. It tests on the K equal to 1. If you want to test K equal to more, then you have to apply here. If K equal to more, then what happens? The magnitude will change, right? So this is K equal to 1, right? So this is K equal to 1. If K equal to 2, then this becomes like this. So this will just expand. This will become like this. The bigger, it will go like this. The phase remains the same. The magnitude will change. Yeah. So this will K equal to, say, K equal to 2. This is like this. Yeah. So this tells you like this is the final in which the K value is not there. So what it tells you, this tells you like this: when you have the GS and then you have one, let us say you have a GS like this one, and then there's a unit feedback loop like this one, right? And then just testing the GS, you are just looking at the GS, you are going to the check the stability for the complete system, the closed loop system. Yeah, got it?
Okay,
Here
sir.
it has nothing
And
to do
sir,
with K. Yeah.
and sir, for 1 plus GS, what does value P equals to 1 and Z equals to 1 tell us?
Okay, that tells you that there is inside this loop, there is one pole and one zero. There will be some zero somewhere. For the closed, there will be somewhere zero somewhere. So 0, 1 0, 1 0 of closed loop system. That it tells you. Yeah. Yeah, got it.
Sir, for the 1 plus GS, we have the zeros as like the above equation is S square minus S plus 1 will be formed.
Yeah.
Sir, for that we have S values 1 plus minus root 3 iota by 2.
Zero closed loop
Does it tell
here.
anything?
When I say zero of not closed loop, I should write instead 1 plus GS. Yeah, we are talking about 1 plus GS. 1 plus GS. Yeah. So see here. In fact, in this case, you can see when this is a special case in which you have the there is a pole on this line itself. Then what we did, we bypassed it and we have seen like that one. So we know that actually there are two poles basically. Actually there are two poles. One is here and one is here, right? So as such, in fact, if you count both of them, so in fact it will be P equal to 2 and hence Z equal to also 2. So that there is no, since this is not encircling. Yeah. Like in this case, we are bypassing it, and hence you are getting in Z equal to only 1, right? Right. So I mean, in that case, you get G equal to only sorry, the P equal to only 1. Now let us see. Let us see this one. Just add this one, 1 plus GS, and see what happens. Okay. So I think it will explain more. So just a minute. So 1 plus GS becomes what? 1 plus, and you get 1 over S minus 1. This will explain, okay? Explain a few things. So what you get? You get S minus 1 plus 1 and divided by S minus 1. Now this is what we're talking about when we say number of poles and number of zero, that really what is the meaning of that. So here, from here we get number of poles, right? So S minus 1, and what we get? S equal to 0, S equal to 1. So actually what you get is number of poles, basically including that point, you get P equal to 2, right? S equal to 0 and S equal to 1. So P equal to 2. Now we have zeros, right? So zeros, you get what? S square minus S plus 1 is equal to 0 is the what? This will give us the 0 value, right? And we get S equal to 1 plus minus root 1 minus 4, 2, right? And what you get? 1 half plus minus half I root 3. You get like that. So what it tells you, half plus this one. So that means what we get, zeros, is somewhere here. This will be the 0, like this one. Got it? So basically, if you count both of them, what we see, there is one pole here, there is one pole here. If it is passes through this, right? So there is one pole here, there is one pole here. There are 2 poles. So hence P equal to 2, and then you have a zeros from here also and here also, to close to, right? So you have Z equal to 2. Hence N equal to Z minus P equal to 2 minus 2 equal to 0. Or hence you have no encirclement of point minus 1. Yeah, you got it? Did you get it? What are you not getting it? Tell me. Okay, just a minute, guys. Facing angle, difficulties, angles 180 and 0. How do we differentiate? Okay, we are then having 2 zeros in the right S plane. So is this method giving us only the stability? Like only a way of checking. Having 2 zeros in the right S plane. So is this method giving us only the stability?
Sir, like happened in this case that Z equals to 1, only one 0 came out.
Yeah, true.
So, sir, but it may be the case that sometimes we are having pole also 0 inside and Z also comes 0. Then because is coming 0, but then there is a possibility that there was one 0 in the closed loop, in the closed loop characteristic equation. Then it would go wrong.
No. See here, we are doing. We are. Let me just delete it. I tell you one thing. We are going to compare 2 things. Yeah. So what are we comparing? We are comparing GS and 1 plus GS. Right? When you have a GS like this one, you know that both of share the poles, right? So if a GS and 1 plus GS, common pole, right? Poles are common in both of them. You agree? So whatever the
Yes,
pole
sir.
is there here, the same pole will be there in that case. Since you have like this, when we are talking about the GS this one, right? Yes or no?
Yes, sir. Yes, sir.
Yeah. Okay. Okay. Now, only thing is, from here you can find out how many poles are inside this, right? If you are given GS, you can find out how many poles are there on the right side. In this case, we are getting P equal to 2. P equal to 2, and hence this will be valid for this also. P equal to 2 for this also, right? And hence you can just see where this the value is. From here we have 1 here, and at s equal to 1 here. Now, looking at this one, what we don't know here, in this case there is no 0 here, right? So no 0. Z equal to 0 for this one, right? But here z equal to, if you say 1 plus we added, we get z equal to 2. Basically, we are talking about not about this, we are talking about this. So whenever we are say n equal to z minus p, we are talking about 1 plus gs only, nothing else. Yeah. So that means if on the s plane, when we have a contour, how many zeros and poles of 1 plus gs it is encircling is reflected here. Yeah. If
So, sir, it
the
will not.
say again.
Sir, it will not include the zero. The other zero, like the other
Other
zero of the GS, because only z equals to 1 is coming from the stability criteria.
only g equal to 1 is coming. Okay, from stability criteria. So this is because we did not count this one. That's why. Yeah. We did not count this because this we bypassed this one. No, that's why it gave you. Okay, that's why. You got it.
Okay, sir.
Yeah, you bypassed it. That's why you are getting it. Otherwise, you but in any case, even if you bypass this one, that tells you that at least 1 is there, right? So in that case, n is equal to 0. It's yeah, but you know that you are skipping this one, and so basically, just I'm looking at this one. As soon as you see that there is a 0 here, there is a pole at s equal to 0, you know that it is not going to be stable to begin with. Yeah.
Okay,
Okay.
sir.
So this is because of the special case. If you did not have this one, then this is a clear, very clearly you can see that. In this case, since you have bypassed this one, hence you get this kind of thing, because the moment you bypass, this point is not included, right? This point is not included. If you include that, automatically your P will increase in that case, right? And hence in that case, G will be equal to 2. Right? So automatically it does that. But in any case, this is unstable because you get automatically, you get, even if you take 1, so you get Z equal to 1, right? And hence it's not stable. Yeah. Okay. So in this special case, you have to add for the one which is not counted. Yeah. See, if you add that, then you get Z equal to 2. Okay.
Okay, sir.
Okay. Any other doubt?
No, sir.
Okay, so did you solve other questions?
Sir, sir, for one more question, I am having doubt.
Yeah.
Question in second
Okay.
question, like how we are doing the y steady state and all.
Second
Like in
question.
first question, sir, in first question and second question, both we have to find the steady state output. But the
Right.
for one system given is closed loop, and for the other is the open loop. First one is open loop given, and the second one is a closed loop. So I am not able to differentiate like how we have to do for which one. Sir, third I want to know.
Okay, method. So no, but here also says first one says consider the unity feedback system with the closed loop transfer function. So in the first one, you have to add that. So the first one, you have the B71. You have to first write 1 plus G, like the closed loop transfer function becomes. You have to first convert that, right? So this is something like this. You have GS here and unity, this unity like this one, right? Okay, so the transfer function in this case, here we have RS and CS, and then
So sir, we'll
RS
make
over.
CS upon RS only, same like for second one.
Say again, say again.
Sir, in second question, they have already given CS upon RS. So for this also, we'll make CS upon RS and then
Right.
output upon input we'll solve.
Sure.
Okay,
That's
sir.
it. That's it. Yes. So simply it will be, as you know, CS over RS equal to GS divided by 1 plus GS. And then you will get that. Yeah.
Okay, sir.
Okay. Any other doubt?
Having questions, I'm not facing doubt, but for the graphs corresponding to those questions, I'm facing problem. Bode plot when it says and all, in that I'm facing problem.
So
But
for
for the
Bode diagram, yeah, you have to, like, you can assume that it is a linear between 2 points. Yeah. So and you have to add them together. So let us say there are three, maybe your, for example, GS maybe look like, say, S plus A over S plus B plus S plus C, something like this one. So what you will do is for all of them, like for GS, that becomes, for example, becomes I omega, A plus I omega, and then B plus I omega and C plus I omega. And then you are going to say A square plus omega square divided by B square plus omega square, and then C square plus omega square. So for all the three things, you can plot separately, like for this one and this one and this one, and then you can add them together. So when you say log of this, 20 log this one, so you take 20 log this one, and hence what you get is 20 log of this. So simply you get 10, basically here 10 log A square plus omega square minus 10 log B square plus omega square minus 10 log C square plus omega square. So you know that you can plot separately. First you plot this one, whatever way it is. Let us say it goes like this one. The other you can plot, which may be going like this, right? The third maybe going like this one, and then you are going to add them. Yeah, so add this and subtract this one. So this one, for example, this will be positive, this will be negative. So accordingly you can plot. So you start with this and the other becomes negative, goes like this, and then add them together and find out like that. Similarly for phase diagram also. So for individual components you plot separately, and then after that add them together, you get that. So those kind of things you have to do. So when you are confused between 0 degree and 180 degree, you have to look at what is sine theta, what is cos theta. You know, so if sine is if the both of them as I was explaining, you have to look see the quadrant, in which quadrant it is. Yeah. So and for a small value, not exactly 0, you see that from which side it is. So omega you can assume very small. And then you will see like that. This current, you know that sine and this cos, right? So sine will be positive, and cos is also positive. Here sine is positive, but cos is negative. Here sine is negative, and the cos is also negative. And here sine is negative, but cos is positive. So based on this, like when you say tan inverse, and let us say you have A over B, depending on which one is what, you will get that. And this is for about A plus IB for this one, right? For this B over, B over A, it will be B over A. So depending on if B is negative, let us say, and A is also negative, then you know that it has to fall here somewhere. Yeah, both of them, let us say, this is also negative, this is also negative, but B is getting 0, right? Then you know that both of them are negative, so it has to be 180 degree. In both the cases, like whenever you have cos is negative, and in that case, see that cos is negative in both the cases. In that case, when you know that A is negative and B is 0, A is negative and B is 0, then you know that it is 180 degree. Yeah. So accordingly you have to. Okay. So did you solve the question 7-16? So this will also.
Yes, sir. Yes, sir.
You did? Okay.
Yes, sir.
This will also make clear a few things, like you know the role of K basically. So K means the gain. So this is the question 7-16, also known as conditional conditional stability. So in which, depending on the value of K, you will have either stable or not stable. Yeah? So if you change the K, then the plot will also change. So just look at 7-16, and after that we will be done. So 7-16, and here we have like this. Yeah, something like this. So we are going like this, like this one, and one is the -1 is here. And the second one we have similar. Okay, so it says there is no GS has no poles in the right half sphere. So there is no poles on the right side. So in this case, what we see is the clockwise and clockwise and anti-clockwise. So both cancels out, n equal to 0 in this case, right? And here we have this is 1 and this is 2, n equal to 2. Also given that there is no poles on the right side, so p equal to 0. So p equal to 0. Hence we can find out z. So n equal to z minus p is equal to z minus 0 equal to, in this case, n equal to 0, right? So equal to 0 and z equal to 0. So you know that no poles, no 0 inside the S contour, and hence this is stable. In this case, we have the n equal to z is z minus p is equal to 2, and hence we know that z equal to 2. So there are two zeros inside the original S contour, hence this is not stable. Okay. Now here we can also see the role of a like conditional stability. Just see, this is not stable, this is not stable, and this is stable. The question is it possible that when you have this, you can change to this one, and how will you do it? That's the question. Question is, if you know that the root locus looks like this one, and you have to make this is not stable, and you have to make a stable, how will you do it? What will be the answer?
So you said that we can amplify it using k. So we'll take a k
Right.
value so
Yeah.
that -1
Yes, exactly.
comes first.
Yeah. So yes, right. Increase the k, and automatically this will be zoom. It is something like zoom in. Basically, when you are zooming in, it will expand. So automatically -1 will shift from here to here. Yeah. And because of that, as soon as it comes inside this one, this becomes stable. So that is the role of k. You can. Yeah. Yeah. Okay. Any other question?
Sir, in previous lectures in chapters
Okay. If there is no other
in
question, yeah.
chapter
Right.
for finding the sigma asymptotes, in those two had told two methods.
Hmm.
One by basic, and the other by the formula.
Number of asymptotes you are talking about.
No, sir.
Number
The
of asymptotes.
asymptote.
Acha, okay. No. There is only one method. I think probably just a minute. So it is not there are difference between. There is only one method. How come you are saying two methods?
Sir, in the other method, you told that the equation of asymptote will come out.
Hmm.
So
Acha,
that was using.
okay.
Sir.
Yeah. So that is one thing,
So,
and then.
so, sir, according to that, the equation should have the same root, like A should be same as that of sigma asymptote. But in chapter 6, one problem, it was not coming similar to that. So I'll mail you that question later.
Okay. Okay. So. So you are saying maybe something like some asymptote we have, like if there are, this may be something like this one, right? So this is the asymptote like this. One of the way that we found out was, you remember, we made like if the GS is equal to S plus A over S plus B, S plus C, something like this one, then the value will be where it meets, that we are talking about, right? Right? You're talking about where it is going to meet, right? Yeah. So that sigma asymptotes are, yeah, so that may be given by simply you say minus B plus C minus A divided by N minus M.
N minus M.
So in this case, 2 minus 1, right? In this case, so you will, in this case, you simply get this only, minus B plus C minus A in this case. So this is what you will get like this. The what other method you are talking about? I'm not getting that.
Sir, you had told that if we are having 1 S plus 2 upon 1 plus like something low and something above, and then we bring it down from above, and then we find by the basic method the equation of asymptote. Like
Acha, okay, okay. Yeah, okay. So the equation of asymptote, basically in that way, I must have just demonstrated basically, So it like what is the meaning of asymptote and all those things. Yeah, so I may have demonstrated that way. Yeah, so not necessarily this is the standard method. It was just to show basically one of the other method also, give you insight, So not only one way, but telling you different ways actually. So not necessarily you are going to get the, you may apply to some others also, but please send me the question. I will look into that. Okay.
sir, might be because I was not able to calculate correctly. I was not getting the answer correct.
Okay.
Similar for both.
Okay.
Okay, sir.
Yeah.
I'll make it.
Okay. So you can try yourself in case it's you are not getting that way. And but like if you are able to do applying this method, just do it. So you don't need to actually solve it other method. So yeah.
Okay, sir.
Okay. Anything
Yes,
else?
sir.
Yeah.
No,
Okay.
sir.
No problem. Okay. Okay then. See you later then.